Hey there, welcome to Axiom. So a lot of you have been asking me to cover L-2.7, round robin, or our CPU scheduling algorithm with example and operating systems, and I finally got around to making this video. Trust me, once you understand this, everything else in this chapter clicks. Let me explain. Okay, let's dive right into this explainer. We're going to uncover the ingenious mechanics behind how your computer manages to literally do a million things at once. It's a fundamental piece of engineering that makes our modern digital lives possible, and we're breaking it down slide by slide. Now, you might think your CPU is running your Spotify playlist, dozens of Chrome tabs, and your background system updates at the exact same millisecond. But as we know, true simultaneity on a single core, well, it's actually a pretty clever illusion. The secret to multitasking is honestly just speed. The processor is rapidly hopping between tasks, so incredibly fast that our brains can even perceive the gaps. It basically gives every single application a tiny sliver of attention before instantly moving on to the next one. Here's our agenda for today. 1. The illusion of multitasking. 2. The ice cream queue. 3. Inside the ready queue. 4. Scheduling by the numbers. 5. The time quantum dilemma. And 6. Fairness over efficiency. Section 1. The illusion of multitasking. So why do we even need to juggle these tasks in the first place? Well, in a time-sharing operating system, responsiveness is absolutely king. Just imagine if your computer used a basic first-come, first-serve setup. Your music would completely freeze just because your web browser decided it needed to load a massive high-res image. Obviously, we need a system that stops any single task from hogging all the resources. Section 2, the ice cream queue. To really grasp how we fix this freezing issue and keep everything responsive, let's look at a highly relatable real-world analogy. Imagine an amusement park ice cream counter. The rule is simple. The scooper serves one single scoop per person. This keeps the whole line moving smoothly without ignoring anybody. If you want a double scoop, you get your first one, and then you have to go right back to the end of the line and wait your turn again. The crucial takeaway here is that a software process is exactly like a person in that line. In the CPU, that's our ice cream scooper, giving everyone a fair turn again and again. This is round-robin scheduling. It's one of the oldest, simplest algorithms in computing, doing exactly this in a continuous cyclic queue. Section 3. Inside the ready queue. Let's peek under the hood. Technically speaking, this is a preemptive clock-driven setup. Preemptive just means the CPU actively interrupts a process. And it is absolutely crucial to note that it's starvation-free. This means no background process gets completely ignored or left hungry. Everyone gets to eat. To enforce this fair play, we use something called the time quantum or time slice. Think of the time quantum as that strict one scoop per turn rule. It is the absolute heartbeat of this entire algorithm. Once your time is up, your turn is over, whether you finish your actual work or not. So what happens when the clock runs out? Every time that quantum expires, the CPU performs what's called a context switch. It's a fast but resource-heavy process where the operating system has to pause the current job, securely save its exact state, move it all the way to the back of the queue, and then load up the very next process so it can begin executing. It's a whole lot of shuffling. Section 4. Scheduling by the numbers. It's one thing to talk about ice cream, but let's throw some actual data into the mix. Here we have 4 processes arriving at different times. They all need different amounts of what we call burst time to finish their specific jobs. And importantly, They're all constrained by a strict time quantum of exactly 2 milliseconds. As you'll see here, this brilliantly illustrates the solution. The Gantt chart shows the CPU switching precisely every 2 milliseconds. Notice how it forces the longer jobs like P1 and P2 to jump back into the queue, while shorter jobs, like P4 right there, are able to jump in and finish their single millisecond of work incredibly quickly. It's beautifully balanced. By extracting the completion times directly from that chart, engineers calculate two massive metrics: turnaround time and waiting time. For our specific data table, the math works out to an average waiting time of exactly 4.7 milliseconds for these four processes. Honestly, that is incredibly responsive. Section 5, the time quantum dilemma. Now, executing this perfectly in the real world introduces a huge engineering headache, the Goldilocks dilemma. If your time quantum is too large, it basically just evolves into a first-come, first-served system, making your computer feel super sluggish. But if you make it too small, the processor just drowns in context switches, and all that overhead completely takes your throughput. So to strike that delicate balance, real-world operating systems typically assign a time slice right in the sweet spot, somewhere between 10 to 100 milliseconds. That's a magic range where you get smooth, snappy interactions without totally drowning the CPU in management overhead. Section 6, Fairness over Efficiency. As we wrap up this explainer, let's think about the philosophy behind why we still rely on this algorithm today. Instead of prioritizing the absolute shortest jobs to boost pure statistical efficiency, or letting so-called important tasks bully the smaller ones, Round Robin treats every single process as an equal citizen. It heavily prioritizes a fair, highly responsive user experience above all else. So while it absolutely creates that beautifully smooth typing, clicking, and browsing experience we demand every single day with zero process starvation, its total lack of priority awareness can sometimes lead to inefficiencies. I mean, it will literally give a vital critical system update the exact same attention as a random background notification. As you digest all of this, ask yourself, how might modern OS designers combine the sheer fairness of this ice cream queue with, say, VIP priority lines to get the absolute perfect balance? Could that hybrid be the ultimate secret to modern computing? Think about that, and keep exploring how these hidden systems shape the technology we rely on every single day. And that's everything you need to know about L-2.7, Round Robin, RR, CPU scheduling algorithm with example. If this video helped you understand the concept better, make sure to hit that like button and drop a comment below telling me which topic you want me to cover next. Don't forget to subscribe to Axiom and turn on the bell icon so you never miss a new lecture. See you in the next one.